frequency deviation. So frequency deviation means what? First of all, you have to write the expression, that is omega I is equal to omega c plus kf gt, which we already derived, we already discussed. That is, this is the expression for instantaneous frequency in the case of phase modulation. Now,
तेज बोलो.
so this is instantaneous frequency, right? So this is the expression for instantaneous frequency, that is omega equal to omega c plus kf gt. So what is the frequency deviation? Frequency deviation is the maximum change in the instantaneous frequency from the average value omega c, right? So so this kfgt will decide that how much deviation will be there. So what is the frequency deviation? I will represent it in the form of diagram. That is, this is your frequency, that is omega c, that is your carrier frequency, and it will deviate either in the positive direction or in the negative direction. So this is the negative deviation, and this is the positive deviation. So this is denoted by delta omega. So what is this delta omega? Delta omega is mathematically expressed as maximum value of kf maximum value of kf. So the sign and magnitude of this kf will decide the maximum deviation. That is, this sign of this kf decide that is whether it's a positive, whether its deviation is positive or deviation is negative. So this expression number, let us say 90. This is the expression for the frequency deviation. So delta omega is nothing but the frequency deviation, and it is governed by the expression kfjt. So the sign and magnitude of this deviation will be determined by the magnitude and the sign of the kfgt. So this is the expression for kfgt, which determines the frequency deviation. So, and it is very important parameter in order to determine the bandwidth of, right? So if you are to determine the bandwidth, we will have to use this delta omega, which is known as the frequency deviation. So what is frequency deviation? The frequency deviation is the maximum change in the instantaneous frequency from the average value omega c. It means how much it is deviating in the positive direction or in the negative direction. It will depend upon the sign and magnitude of kfgt. This is the frequency deviation, and it is very useful parameter for determining the bandwidth, right? Now, so accordingly, let us take an example that how we can determine the frequency deviation. So let's take an example of it. This is an example. Suppose if you have a signal ft. Example, that is, we have a signal ft. Let us given that is a signal of a single tone modulating signal. Right? That is a single tone modulating signal ft is given by the expression em cos omega mt, right, is frequency modulates a carrier a cos omega ct. So what do you find? So find frequency deviation. So this is the example, this is the question which you have to solve. That is, a single tone modulating signal Ft is equal to Em cos omega mt, which is a frequency modulated signal. It means it's a frequency modulates the carrier a cos omega ct. So find frequency deviation. So we have a single tone modulating signal. It means we have a single tone modulating signal means we have single tone baseband signal, and it's given by Ft is equal to Em cos omega mt. So, and it is frequency modulated signal, and its frequency is a cos omega ct. So to find its, we have to find the value of frequency deviation. So how we calculate it? We know that the value of delta omega is equal to what? Mod of kf ft or gt maximum, right? So first of all we will write the value of this, that is kf em cos omega mt. Now here in this expression, this is the expression which you derive for the frequency deviation, and in this expression we have put the value of ft, which is given as em cos omega mt. So the maximum value value or amplitude of cos omega mt is equal to 1 here, right? So here this delta omega comes out to be what? Kf em. So this is that's how we can find the value of frequency deviation. And what is the value of kf here? The kf is equal to delta omega upon em upon, right, em radians per volt. So that's how we can find the value of frequency deviation, right? So here we understood the example of a frequency deviation, that and how we can find the value of a frequency deviation. So what we have done, first of all we have wrote the formula of frequency deviation, delta omega equal to mod of kf ft maximum, and here the value of ft is equal to em cos omega mt. So we put that value here in this formula, and the maximum value of cos omega mt, the maximum value of this certain signal is equal to 1 here. So here only one term will be remain, that is kf em. So this delta omega will be equal to kf em, and em, right, this is the maximum value of this frequency deviation, and here kf is equal to delta omega upon em, which is in radians per volt. That's how we can find the value of a frequency deviation. Now we are going to discuss about the types of FM on the basis of this frequency deviation. So let's move ahead. So now we are going to discuss, that is types of FM. Types of FM. Now, as we already discussed, that this frequency deviation is very useful parameter in order to determine the bandwidth. So, and it is governed by the KFGT. If KFGT is large, the bandwidth will be large, and if KFGT is small, the bandwidth will be small. So here the KF, this phase sensitivity, is the parameter which is governing or controlling the bandwidth of frequency modulated wave, right? So here we are going to discuss, that is how many types of FM which are there. So as you first of all you have to understand, that is the frequency deviation is that parameter which is very useful for determining the bandwidth of an FM signal. So if the value of the KF is large, the bandwidth will be large, and if the value of KF is small, the bandwidth will be small. So accordingly, there are two types of frequency modulated signals are there. That is, two types of modulation is there. Narrowband frequency frequency modulation. It means on the basis of the bandwidth, there are two types of modulation. That is narrowband frequency modulation and the wideband frequency modulation. So first of all, we have to understand that is this delta omega is that factor which determines the bandwidth, right? And this delta omega is equal to what? this delta omega equal to kfgt. So here, this, which thing is governing the bandwidth? This kf. So kf, the bandwidth is controlled by which parameter? The bandwidth is controlled by the bandwidth is governed by kf. So if the value of kf is large, the bandwidth will be large. If the value of kf is small, the bandwidth will be small, and if the value of kf is large, the bandwidth will be large. So accordingly, there are two types of FM, that is, first of all is narrow band FM, that is NBFM, narrow band FM. How? Here, what will be here? Kf is small, so bandwidth is narrow, and accordingly it is known as the narrow band FM. The second one is wide band FM, that is wide band FM, that is wide band frequency modulation. Here kf has an appreciable value, so FM has wide bandwidth, so accordingly it is known as the wide band FM. So on the basis of this value of kf means the frequency sensitivity. If the frequency sensitivity is small, the bandwidth is narrow, then the frequency modulation is known as the narrow band frequency modulation. And if the kf has an appreciable value, so FM has wide bandwidth, and accordingly your modulation, that is frequency modulation, will be known as wide band frequency modulation. So let us move ahead. First of all, we will discuss about the narrow band FM. And we will write the expression for the narrow band FM first of all. So first of all, let us discuss the narrow band FM. Narrow band FM. So first of all, we will write, that is how we can represent the FM wave in the form of a phasor. So we can write it in that way: psi FMT is equal to A e to the power j omega ct plus kf g. We will write it in that way. This is the expression for the FM wave. Now suppose, let us say this is equation number 19. I am again writing it. So in this expression here, for as we are discussing about the narrow band FM, here the value of kf gt is much more, very less than 1 for all values of t, right? So here we can write, we will take that part, that is here A e to the power j k f g t will be almost equal to 1 plus j k f g t. It's your equation number 20, right? So now we will include this value in the expression. That is, now this expression for the phasor becomes phi fm t is equal to a 1 plus j k f g t multiplied by e to the power j omega ct, multiplied by e to the power j omega ct. Okay, so now what you have to do, if you will expand this, in that way, that is, now it comes out to be this 5 mt will be equal to a. First we write the part which is there, that is, we write 1 plus j k f g t multiplied by a j omega ct means cos omega ct plus j sin omega ct. So we write here cos omega ct plus, again because this place is less, I will write it in that way, that is a 1 plus j k f g t. So I am expanding the e to the power j omega ct, which is equal to cos omega ct plus j sin omega ct. Right? So now, if I will multiply this expression, then I can write it in that way, that is a cos omega ct means this one, so whole expression will be like this, cos omega ct plus j sin omega ct, okay, plus this jkf plus, I am writing it here because the space is there, that is plus j k f g t cos omega ct plus j square k f g t sin omega ct. So you just look at this expression, that is, first of all what I have done, I write the expression, that is we already derived, that is how we can express FM wave in the form of phasor. So I have proved the expression for it, that is psi fmt is equal to a e to the power j omega ct plus kfgt, written as equation number 19. Then I have written, that is, for NBFM the value of kfgt will be much more less than 1 for all values of t. So I have written a to the power j kfgt is almost equal to 1 plus j kfgt, which is equation number 20. Then I further expanded this expression, that is 5mt is equal to a 1 plus j kfgt is equal to into e to the power j omega ct. Then I further expanded it, that is a multiplied by 1 plus j kfgt multiplied by, here I have expanded e to the power j omega ct, that is cos omega ct plus j omega ct is equal to a cos omega ct plus j sin omega ct plus j square kfgt sin omega ct. Now I am writing the expressions which are there above here. So I'm just erasing the expressions. I hope you might have noted down, understood it. So I'm writing it again, that is 5 bar fmt will be equal to, now I'm writing it here, that is a will be as it is cos omega ct plus j sin omega ct. I'm writing it here again. I'm writing it here. Why I'm writing it? Cos omega ct plus j sin omega ct plus j kf g jkfg cos omega ct plus j j square k f g t sine omega ct. Now I just erase this expression which I have written below. So now I'm erasing it. I am phi bar f and d is equal to a cos omega ct plus j sine omega ct plus j k f g t cos omega ct plus this j square means minus is equal to minus 1. So here in place of this j square I will write minus sign. So kf gt sine omega ct. Now you have to understand this phasor of this fm, we only consider the real part. So we will have to discard the imaginary part. It means wherever there is a j there, we'll have to discard it. We have to remove it. We have to, okay, we will not take it into consideration. That is, so now this expression. So what we will do? We will not take this value which contains j. That is j. Wherever there is a j, we will skip those values. So now this expression will become a cos omega ct minus kf gt sine omega ct. Now let us multiply this expression by a. So now this whole expression will become a cos omega ct minus a kf gt sine omega ct. Let's say that's equation number, yes, this is expression for what? Sine fm. This is what? This is the expression for what? This is an expression for the NBFM. This is an expression for the NBFM. So I will again write this expression. This is the equation number, whatever the equation number there which is there. After that, so I will clearly write this expression here, that is phi f m t will be equal to a cos omega ct minus a kf gt sine omega ct, and this is an expression for the NBPM, that is your equation number 21. It's representing the equation for the NBPM and the same NBFM, sorry. And similarly we can find the expression in the same manner for the NBPM. So this is the expression for what? For NBFM. Now in the same manner, I'm writing it here, that is for NBPM, that is narrowband phase modulation, we can find the expression which can be mathematically expressed as psi pmt is equal to psi bar pmt is equal to a cos omega ct minus, in place of only the constant will get changed, that is minus akp ft sine omega ct. So in the same way, this is equation number 22. This equation number 22 will represent the expression for the NBPM. Equation number 20. So what we have discussed, that is how we can find the expression for the narrow band phase modulation. That is, and it comes out to be phi bar fmt is equal to a cos omega ct minus a cap gt sine omega ct. And in the same manner, we can find the expression for NBFM, that is phi bar fpmt is equal to a cos omega ct is equal to a kpft sine omega ct. This is the expression for the narrowband FM and the narrowband PM. Now you have to remember this, that is here the bandwidth is very similar to AM, and here we are using the sideband and carrier terms, and we have to also understand that is this GT is very similar to the FT, that is the bandwidth of GT, and FT is very similar. And we know what is GT. GT is given by integration of ft dt. You know that. So if you find the Fourier transform of this GT, it comes out to be 1 upon j omega f of omega, and in other words we can say that fg of omega, it is equal to what? It is equal to 1 upon j omega f of omega, right? So let's say it's the question number 23. So to understand this, is if f omega is limited to what? Limited to omega m, then this g omega will be also restricted or limited to omega. You have to understand this. So you can clearly see that is this the very GT and FT is very similar. That is the bandwidth. If f omega is limited to omega m, then j omega will be also limited to the omega m. So you have to understand this. That is here the frequency component which you use for the amplitude modulation, the same frequency component which we are using for the frequency modulation. So that's how we can understand that is what is the narrowband FM and what now. So what we have discussed, that is what is how we can find the expression for the narrowband FM, and what is GT and FT. So GT, the GT and FT is almost very similar, and if you find the Fourier transform it, we can find the expression in this manner. And we have to also understand this, that if f omega is limited to omega m, then this g omega will be also limited to omega m, right? Now, and also to understand this, that is we can here in this case very similar to him, we are using the carrier terms and the sideband terms. The only difference between this the AM FM here, that is here the amplitude is constant, and here there is a different relation between the sideband terms and the carrier terms in the PM and FM, right? Now let's try to understand that is how we can generate the narrowband FM. Generation of narrowband FM. Generation of narrowband NBFM generation. Now here, like in the DSBSC generation, like in the amplitude modulation, what we are doing, we are generating the carrier and we are also using the balance modulator for using the sideband terms. Similarly, in this here we will adapt that approach. That is, here we will use that. First of all, I am drawing the block diagram of it. With the help of it, you can understand that is how we can generate the NBFM. That is, first block will be carrier generator. The first block will be carrier generator, and this carrier generator will generate the carrier, and then it will go towards the where here. It will go towards the 90-degree phase shifter. 90 degree phase shifter. So you will get the signal, that is, and after that it will go towards the balance modulator, and here from here it will go to this summer. We will get this. Okay. So here, okay. क्या हुआ? बना लो ना. चलो उसको बंद करो, फिर से स्टार्ट करें. Let's discuss that is how we can generate the narrowband FM. That is generation of narrowband FM. So like we are in the DSBSC generation, we are using the balance modulator for producing the sidebands, and we are adding them into the carriers. We will follow the same approach here. First of all, we will use the carrier generator. It will generate the carrier. Then it will move towards the 90-degree phase shifter. 90-degree phase shifter.